let's start with the conservation of kinetic energy in Navier-Stokes equation. Right, we know energy is conserved. But is kinetic energy conserved? In a viscous flow? No, right, it dissipates, right? How much does it dissipate? The viscous strength tensor, that's responsible. I mean, what does viscosity mean? Viscosity is like the molecular motions that mixes fluids, right? So the molecular motion basically converts kinetic energy, which is what we are looking at here, into internal energy, into heat, right? So if you look at the Navier-Stokes equation and basically look over a box where there is a boundary layer goes in, another boundary layer goes out, how much kinetic energy is lost in the volume? The rate of kinetic energy dissipation within this volume can be represented as an integral over the whole volume. The viscous strength tensor operated on the velocity gradient tensor. It's kind of the multiplication, the item by item dot product of these two tensors. Okay, so this is how much the tau is transforming the kinetic energy into heat. Right. So you can figure this out by looking at the Navier-Stokes equation. So partial u partial t plus u dot grad u plus grad p is equal to divergence of tau. And to figure this out, you basically just multiply u dot the entire left hand side is equal to u dot the entire right hand side, right? And then you integrate over a domain. So let's say if we are looking at steady state Navier-Stokes equation here, this goes away, and you are left with these two terms on the left hand side, right? Okay, and then let's look at this term by term. So the first term on the left hand side is u dot with u dot grad u times dx. That can be converted into integration. You need to combine this with let's see, what do you need? You need to combine this with the divergence of u equal to 0. This goes into the divergence of u times half of u dot u dx. So this term can be viewed as a flux of kinetic energy. So this integrated over the whole volume is equal to integration over the surface of the volume, n dot u times half of u dot u ds, right? So this is the flux of kinetic energy through the surface. And this term, integration of u dot grad p, can be integrated by parts. Again, if you combine this with the divergence of u equal to 0, this can be converted into integration of the divergence of u times p, and that through the Gauss's theorem becomes n dot u times p. What is that? That's the work done by the pressure, right, on the surface. Now the last term is the only term that cannot be converted into a surface integral. It has to remain into two terms, right? So one term you have to integrate by parts. So if you integrate that over the volume, integration by parts is gonna give you two things. The first thing is a surface integral of what? Surface normal dot with u dot tau. So this is the surface term, and the integration by parts is going to give you another term that is tau times double dot with grad u. So this is the term that appears as a dissipation of kinetic energy. While the first term is what? What is the first term? Yeah, it's the work done by the viscous shear on the volume, right? So that's the term that we looked at in one of our homework questions, right? So where does the energy come from when you have a viscous flow that satisfies a stagnation point flow, and that the energy comes from this. Okay, so in that case, actually, these two terms balance each other exactly in the homework question. So basically, the key point is that all the other terms can be written as a surface integral that balance with the kinetic energy dissipation. And let's apply this to such an omega that is bounded by two vertical lines orthogonal to the wall, and the wall itself, and a top wall that is parallel to the surface, to the wall. So now, also thinking about the thin layer approximation, that is, the different velocity gradient has different magnitude. So in a thin layer equation, so let's go with the green, blue actually. Thin layer equation, the integral of tau and grad u can be approximated by the dominant term, which is partial u partial y times tau xy. Double dot means tau xy times partial u x partial x plus, sorry, right, so tau xx, tau xy, partial u x, partial y, plus tau yx, partial u y, partial x, plus tau yy in a two-dimensional world. And if you have 3 dimensions, there are 9 terms, basically multiplying the corresponding entry of a tensor with the corresponding entry of another tensor. All right. So here, the only term that is significant in all of these is the x. So now, specialized to the thin layer equation, we have these 3 terms considered on all the 4 sides. Okay, so basically on the left side, let's look at all these terms. So on the left side, integration over the surface is basically integrating from 0 to ye, right? So let's say this is y equal to 0, this is y equal to ye, and this is x plus delta x. Okay, on the left hand side, we are integrating the u dot n, which is basically u in the thin layer equation, times half of u square, right, times dy. So this is what is coming in from the left, and because n is pointing towards the outside of the domain, I have a negative sign here at x. Over the right side of the domain, and the surface normal is pointing towards your right, so I have a plus u times half of u squared dy, right? So at the bottom,
That's at the right side.
that's towards the x plus delta x, right? Towards the bottom, I have no wall normal velocity. So what I get is 0. How about the top? The top is integration from x plus x delta x, right? So the n dot u is gonna be what? My v, right? Is the upward velocity, because at the top my first surface normal is pointing upward. So n dot u is gonna be my v velocity. But it is still multiplied by 2 half of u squared, because this is u dot u is mostly u squared, right? So u is a lot bigger than v in the thin layer equation. Dx. So this is my first term. This is this. All right.
That's a ye.
At ye. Okay. And my second term is the work done by the pressure. And in thin layer equation, pressure is uniform, right, across the y direction. It's not going to be uniform as you're changing x, but uniform as you're changing y. So I can pull the pressure out. Pressure times integration of again from 0 to ye minus u dy plus, so this is at x, plus p times the same integral u dy at x plus delta x. All right. And at the bottom again, the force done by pressure is 0. And at the top, I have some work done by pressure, right? So it's basically P times V dx. Now, if you look at the okay, so let's keep this here a little bit longer. So this is at ye. All right. Now, the remaining term is the viscous effects. So this is, it has to be balanced by the work done by the viscous force. So n times u tau. All right, and also the dissipation. So looking at the work done by the viscous force through the faces, how much is that? So on the left side, which component are we looking at here? On the left side, remember, n is pointing horizontally. V is also pointing mostly horizontally, right? Right, so we are basically looking at tau xx here, which is negligible, right? Okay, and on the right hand side, the same thing. We are also looking at tau xx. At the bottom, which is the wall, what are we looking at? We're looking at tau xy, but we have 0 velocity, right? We have 0 u here. So even there is a lot of viscous forces, it is not doing any work. And on the top, still tau xy, but u is not going to be negligible, right?
Xy is 0. Isn't tau xy 0 at the top?
Tau xy is actually equal to 0 at the top surface, because I don't have any velocity gradient there. It's already outside the boundary layer. So this whole thing is negligible in a control volume like that. The only term we have to balance is the dissipation. So let's write this out. Now it's an integral from 0 to ye, and also integral from x to x plus delta x. Tau xy times partial u partial y dx dy.